So today we're going to discuss inertia. And the idea of inertia is very central to physics. And it, it seems to me that it's not very well explained and that people don't really have a really solid understanding of the word inertia. And it's one of those elusive philosophical things that is sort of like defined very technically, but we don't really have a sort of intuitive sense of what it actually means in physics. And we're going to sort of like motivate this idea, and we're going to first start with the etymology of the word inertia, and we're going to go through how it's used in physics. And here we have, to begin with, we have the ancient field equations. And these equations are equations, we talk about a radical way of thinking about inertia. And basically, the way we think of inertia in this sort of like framework is a natural motion of objects in a curved space-time, which is a radical idea. How is it that we could have something similar to space-time, which is so elusive and so natural to our motions and the state of everyday objects, which could possibly be curved, and that will be tied to inertia? But that's actually very simple. We think inertial motion, is a natural motion of objects in the presence of a curved space-time. And the way to really think about this is in this way. Suppose there's an elevator. And here I'm really referring to the equivalence principle, which is foundational to general relativity. If there's an elevator which is accelerating, the principle states that this acceleration produces physical effects which are identical to acceleration, which are identical to gravitation. So these effects are due to acceleration, which I'm going to notate A, and an observer in this frame of reference, which is an accelerated frame of reference, is going to accelerate bodies falling in the opposite direction. But if you really think about this, let's say the previous position of this body, which might be a ball or any kind of spherical body of a given mass, it's just going to follow the motion, which is sort of like anti-parallel, or sort of like anti-symmetrical to the acceleration. But isn't that due to inertia? And this is something which is going to be very clear by the end of the video, that what is really going on here for this body to move in an accelerated motion in the opposite direction to the acceleration is really due to the body's inertia. Because let's really think about this. There is a background to this. So here we have sort of like the ancient field equations, which we're not going to explain in this video, so I might as well erase them. But what's really going on is that there's a background space-time. And what we mean by space-time is it's a set of rulers and protractors and clocks. You know, every single point in space-time is really defined by a clock. Because an observer might be here and would measure the time, and you have sort of like a time gradient across the space-time. But what's really going on is that the box has moved. You know, the previous point, the previous position of the ball in space-time, or I might say the previous position of the box, might have been maybe this position, you know, which we're going to sort of like have in this dotted fashion. It has now moved to this new position due to the acceleration. And the very fact that this would be the case is independent from the fact that this ball has a position which is correlated in space-time. And you might notice that there's a difference in distance, which is measured by the background space-time, which doesn't move relative to objects. But this distance is actually maybe identical to the box's motion. So we might label this distance d, label this distance d. And here we're sort of like getting to the heart of what people want to mean usually by inertia in physics, is that this ball really want to persist in its motion in space-time. That is to say, Newton's first law of motion, that a body persists in its state of motion. And really what we mean by that is a mathematical statement about the state of motion of the body with relation to forces. And I'm going to just read the statement, and it's the first law of motion. It's Newton's first law of motion, I believe. I might stand corrected. I'll check by the end of the video, and I'll make an amendment if it's not the case. But there's only 3 laws of motion. That's probably the first one. And really the way it goes is a body persists in its state of motion, and I'm going to highlight state of motion because there's a nuance there to really be sort of like kept in mind, unless acted on by a force, you know. And there's no force acting on this ball, so it's going to persist in a state of motion. There's no reason why it should sort of like move with the box, because there's no force acting upon it. It's not in contact with any of the boundaries of the box, and there's no gravitation, there's no electrical forces acting on it, so it's going to persist in a state of motion. And a state of motion, which it was initially in, is basically rest. And rest is an inertial state of motion. And in terms of inertia, we're going to distinguish between really 2 kinds of motions. We're going to distinguish between rest, a state of rest, and we're going to distinguish also a state of inertial motion. So we're going to say, okay, constant velocity. So if a body has a constant velocity or is in a state of rest, well, really what we mean is that the body doesn't have any forces acting on it. And I think it's really interesting to consider that there is a kind of an analogy between the geometrical aspects of these 2 kinds of motion, because rest is really equivalent to a dot, and constant velocity or inertial motion in terms of like a velocity which doesn't change is really represented by a line. And it would be the case sort of like in space-time, but also in a space-time diagram, if you were to sort of like represent this motion in 1 dimension, it would look like, in 1 dimension of space, it would look like just a line. And that's really what inertia is. Inertia is either rest or constant velocity. And it's correlated with Newton's first law, because the law states that unless there's a force acting on the object, it's not going to move. There's a force acting on the elevator which makes it sort of like go up, or the box, and there's no force acting on the ball. Therefore, relative to the object, the ball is going to be perceived by an observer inside the box to move. And this is the genius of the equivalence principle in general relativity, is to notice that one of the effects of inertia is that gravitational effects are perceived by observers in accelerated frames of reference, which is a direct consequence of inertia. You see, because objects in the field of the box, objects in the vicinity of the box or inside the box, have a direction, a uniform direction of motion, which is an accelerated motion. And there exist frames of reference where an observer is going to perceive these effects as totally identical to gravitational effects. And that's really the heart of the equivalence principle in general relativity, which is, by the way, what it's based on. And something really strange what happens is that let's say if there's a light ray which sort of like enters the box at a specific time t, then the box would have moved, a little bit higher at a specific time t1, and at t2 it would have moved again, and it would have moved again in such a way that the perceived motion of a light ray in the box, inside the box, would be curved, which is a prediction from special relativity, which directly sort of like follows from the equivalence principle. But this is a very advanced example, and we don't really need to use these complicated examples from general relativity. We can create or consolidate a really solid understanding of inertia from just looking at classical physics. And I'm referring specifically to classical mechanics in this way. So this is really inertia. The first law of Newton states inertia. A body is going to persist in a state of motion unless acted upon by force. So the idea of a force is very crucial to inertia, and force is correlated with acceleration. So the sum of the forces acting upon the object is going to be equal to an acceleration. It's going to be correlated with an acceleration. And an acceleration is a vector quantity, and so is force. And mass is sort of like a relativistic invariant, and it's a scalar, and so it's not a vector. But what really we want to notice here is that something follows, is that if the sum of the forces, if the sum of the forces is equal to 0, then from this, so we're going to note this formula, which is sort of like the fundamental law of motion for classical mechanical systems. And in the case where the sum of the forces is equal to 0, then acceleration is equal to 0. And acceleration is equal to 0. So this directly follows from this law, which is, I think, Newton's first law, which states that the acceleration a body is going to experience as a result of a force is proportional to the force and proportional to the mass of the objects, or anti-proportional to the mass of the object. And what really follows from this is that if there's no force acting on the object, this side of the equation is going to be equal to 0, and so is this side of the equation also, because it's an equation. If I change this side of the equation, then I have to change the other side, but things are still equal to each other. But the mass is something invariant, so the mass is going to stay. There's no transformation, or there's no change of the state of motion which is going to annihilate the mass. Therefore, I have to conclude that the acceleration is 0. And so this law sort of like further articulates the principle of inertia. And the principle of inertia is really a deep principle in physics, because out of the 3 laws of mechanics, the 3 fundamental laws of classical mechanics, 2 of the first laws, two of the out of the 3 laws are dedicated to articulating this concept of inertia. So I think it's really worth emphasizing how central this idea is to physics. And we're going to look at another example. So we've already said that inertia is either rest or constant velocity, motion at a constant velocity in a straight line. And the reason why that would be the case is because if you think of an object which is going straight, which is traveling sort of like along this line. Let's say this ball is traveling across space in sort of like one dimension, and at some point, for whatever reason, the object sort of like deviates and now travels across this direction. Well, the first law of Newton states that the object is going to stay in a state of motion and it's acted upon by force. Well, this implies that at precisely this point, there's an influence, you know? It might be sort of like an attractive influence. FA for attractive, or it might be maybe a repulsive influence. But there's a force which perturbs this motion, which was supposed to linearly follow the state of inertial motion, and this force deviated the motion of the object. And so this really sort of like emphasizes the law which states that in order to change the state of motion of the object, whether it is to make it stop, sort of like changing the velocity of the object, I want to change this magnitude to another magnitude, potentially 0, or I want to sort of like make it go in another direction, or I want to change its direction by deviating the object.